All right, well, welcome back. It's good to see everyone back here today. Um, I really liked what I saw in the lab yesterday. As I mentioned, I thought it was going to be just a let's figure out the technology, let's figure out the teams as we start all the lab processes this semester, and it seemed to go really well. Least from my perspective, I was really enthused with what I saw. Teams getting started, teams sorting out how they were going to actually get work done, and if anything, I would say more progress than what I would have predicted or expected for that first week. So that's wonderful. Let's keep up all that momentum, and I'm really looking forward to seeing what teams are going to be able to come up with. There was a question about recording of lectures, and Matt, I appreciate the question. I'm back on Canvas here on our schedule page. It's viewable right from the home page. You just click on schedule, and you get this. As someone, I won't say who, referred to this as 1990 HTML, which it is. That's fine, but so old school HTML web page here. It works for me, so I use it. And when you click on the individual weekly topics, as we start to fill out those topics, you're gonna be able to find pretty much what you would expect. So the actual PDFs for the lecture slides are there. You are very welcome to have those handy. And follow along directly with your own local copy. You also don't have to, but I think it's not a bad idea to do so. And after each lecture, I just upload to YouTube the recorded video, so you can see that for Tuesday's video already. And then occasionally on a weekly basis, I'll upload just a little separate one-off. Now remember, there's no exams in this course, so don't feel that you have or are compelled to watch every single minute of video. I'm not gonna hide exam, questions in any extra video or anything like that. But just for example, for this first week, I thought, well, if you have syllabus related questions for the course, I just made a quick little, I think it was 11-minute video, just going over the syllabus. It's already covered with what we talked about on Tuesday, but then you have one place to see it in that separate video. So that's what you'll see on a week to week basis in that schedule page on Canvas. I tend to stay on top of that, but let me know if I've neglected something, and I will be sure to add it there. Going back to that schedule, though, I definitely wanted to talk about what is upcoming in the class. So we have these lab assignments, and if you look at the timeline for them, the Canvas assignments timeline, they're basically 13-day assignments. That's intentional. And what my goal is for the class is for us to come together on that Tuesday that they're due. The assumption that if you're not done with it, you're just finishing up and just doing some final report writing and things like that before you've done your final submission. And we come together as a class. And so I have those listed on the schedule as demo days. I love demo days. I don't have to do anything. I just kind of show up. Those are my favorite days, of the semester. And we're going to have one for every one of our lab assignments. I think the timing works out pretty well for us, although I won't require that every team go, certainly if we run out of time on a given Tuesday. But if we have the 8 teams, and if I say, 10 minutes is probably sufficient to talk about your design in front of the rest of the class, that gets us to 80 minutes, and that's probably good. If we get to 7, that's fine. If we have a wonderful, deep discussion about one team's project or one team's lab, and we only get to 6, that's also fine. But that's what's going to happen on those Tuesdays. So that first Tuesday, February 9th, will be our MP0 demo day. And assuming my initially planned schedule continues, it will continue with every 2 weeks on that Tuesday being our demo day. And I'll add more detail. I was planning on waiting until teams got a little bit more progress and could start thinking about, getting ready for that day. That is part of the grade for the lab. It's going to be a binary thing. Did you come? Did you participate? Did you describe what you did for your MP assignment on that Tuesday? Um, but I'll want students to present on those days. Those will be your days. I'm here to ask questions, kind of shepherd the whole thing through, but those are going to be your days to discuss amongst your peers what went well, what was a struggle, what kind of fun things did you do for that particular lab assignment. Um, Creating slides is probably a good idea. So if you throw together some Google Slides and send me a link, I can also just kind of run through them on my screen here. The question about recording becomes an interesting one in this online format for these student demos of projects. The way I've been recording right now would not work if you are the ones presenting for those. So I may wind up just doing a Zoom recording for that. You'd have to feel comfortable being recorded and put on our class unlisted YouTube channel for those. I think the benefit is there. We could also collectively decide if 10 of you tell me, I just don't want to be recorded for that. That's also okay. They don't need to be recorded. This isn't going to be shown to anyone in future generations. Uh, but that would be my plan by default. So I'm open to suggestions as we get closer to that February 9th initial date. Um, Certainly makes my life easier to record those. But if nothing else, I would get a copy of whatever slides or other materials you'd be presenting. Don't overthink that when we get to that point. 10 minutes will go by very quickly for a project that you've spent 2 full weeks working pretty hard on. You would just be talking about, what different roles the team members had, what challenges you faced, how you overcame them. You've drawn diagrams, or you will be drawing diagrams for your lab report anyway. Just kind of walk through those diagrams. If you think you did something interesting in terms of, you made a cool simulation test bench, or your design uses a clever VHDL trick, show that off as well. And those 10 minutes, including some Q&A at the end, will go by extremely quickly, for each team. Before I move on to getting back to our learning module number 1 here, any questions about that? You can speak up, or you can also just post in the chat. Any questions about schedule in general or that upcoming MP0 demo day? If it comes due in a couple minutes, you can always post it, and I'll come back to it as we go. So that is our schedule with the rough timeline of our topics as we're covering them. I'm certainly including what I was calling time for sort of checkpoints, but because of what would be happening that week. Again, even though we're not having exams or anything, it's probably just a catch-up week for us. We won't necessarily have to cover new ground in that given week. And this is the layout of my initial plan for what I want our learning modules to cover this semester. It does match what's on that schedule page in Canvas. It's a direct connection between the two. So we're in the introduction. I think we have some fun stuff to cover today, but just let's get motivated to kick butt in this class. That's my goal for this week, and maybe we haven't done that yet, but we're getting there. We have the rest of the time available today to do so. Next week is a little bit of a smorgasbord of things that I think you need to know that you may already not know. Some of you may not already know. So I just kind of lumped those all together and called that enabling technologies. Just some fundamental considerations for computer graphics that may be very obvious to some, but for others, it's good to know that first. And likewise, for the digital design aspect of our lab experience, some fundamental building blocks that, again, some of you may be very comfortable with, but I think a lot of you kind of falls in the cracks of your other classes and you wouldn't really have gotten much exposure to. So that's a bit of a weird topic in the sense of I'm just trying to cover a lot of ground, and we'll focus on the parts that I think there's more interest. So if I get lots of questions about a particular subtopic, we'll dive deeper. I put a lot of material in there, but we don't have to actually cover all of it at any level of depth. Then we'll move on to sort of an OpenGL boot camp. The tricky part about that topic is this is not an OpenGL course, right? This is not Introduction to Computer Graphics. It is that in the sense that you need to have some of that material to be able to understand graphics processing and architecture, and you'll be working with OpenGL for your labs. But we'd really have to spend almost an entire semester if this was to be an OpenGL class itself. So I'll go through the boot camp approach. Your juniors and seniors, and some of you graduate students, you should be able to handle programming in OpenGL. It's not incredibly difficult. It has some weird quirks to it. I'll talk about some of those. You'll be just fine once we've gone through that boot camp together. And then we're really going to start jumping then into more of the processor and architecture topics after that LM-03 there. The graphics rendering pipeline is very much mapping of graphics algorithms to hardware, some of the fixed function hardware, and that will coincide with the lab where you're building a lot of that fixed function hardware. And then when we talk about these other aspects of very conventional sounding graphics programming topics like viewing and transformations, textures and lighting, we're really going to be talking a lot about them from the architectural perspective. We have to cover just enough algorithms to understand what we're talking about, enough of the math to understand what the actual need is from an architectural perspective. And then as frequently as possible, we'll be diving into the architectural implications. And that's very much the case when we talk about programmable shaders. We could have an entire semester where we just talk about shader language and how to write really good shader programs. We'll do just enough to have fun with it, and then we'll look at the architectural underpinnings of what processor pipelines those shaders are actually running on. Then finally, after we get past sort of the traditional graphics and programmable graphics topics, we'll start talking more about GPU computing. I would also add, and maybe it's a symptom of trying to do so much and give you so much information this semester, we could certainly have a whole entire class on GPU computing as well. That could very much fill an entirely different class that is just doing CUDA programming and building our way up from basic concepts all the way to full fledged parallel applications. That would also be a fun class to teach. I think if you're interested in those, your best bet is to look at what Iowa State refers to as their parallel computing or high performance computing courses, the 425s, 426s, I think 424 as well. You may wind up learning some Fortran along the way, or depending on which variant of that class you take. But you'll get some more exposure to doing hands-on CUDA programming in those classes for those assignments. And then finally, when we look at our topic, our module outline here, I leave that last part for what are some advanced rendering techniques, and what are some of the architectural underpinnings of those. Uh, I have to do some studying up on that as well because that's changing almost on a monthly basis. But algorithmically, there's a lot of very fun things, and then architecturally, that's starting to seep into what you can buy in commodity graphics processors. So that's our schedule. And then finally, I didn't get the chance to mention it on Tuesday, although it would have been a better fit for Tuesday's class. Just sort of the final syllabus items here in terms of how your grade gets calculated in this class. Um, it's a hands-on class. So these machine problems, of which there are 5, is worth the majority of your points this semester. And if you include the final project as really just an extension of that same experience, it's worth 90% of your score this semester. Some people are enthused by that. Other people are intimidated by that. Definitely enthused is what I was going for. That was my hope here. That you should be fine if you're the kind of student who enjoys doing hands-on labs and projects and enjoys building things from in the computer engineering sense of the word. You're going to do just fine in this class. You're going to enjoy this experience, and you're going to learn a lot, and you're going to do fine from your grade. I reserve that last 10% really just for good course citizenship. Just refer to it as class participation. I'm not taking attendance on a day-to-day basis here. I don't want to have to deal with that. But I'll know if you've been in participation. Have you been coming in lab? Are you participating as part of your team? Are you coming and doing the demo day experience for your team? Um, when someone posts a random question on Discord, are you also, uh, contributing to that question or possibly to the answer as well? Or are you just part of the class? Do I know who you are because you've been participating both, in class and outside of our class times this semester? That should be a very gettable 10% as well. This caveat I already mentioned on Tuesday, but I just want to reiterate that. Um, I think that phrasing is pretty good. We're balanced on the cutting edge of some relatively fragile technologies. So both by intention was for this not to be entirely smooth every step along the way. Things could fall apart in terms of the technologies we're balancing all of our lab infrastructure on top of. It's going to be okay if that happens. I want this to be a challenging class. I don't want this to be an overly stressful class. And hopefully you can differentiate between those two sets of feelings, that you're busy, that you're working on interesting things, but it shouldn't be your source of stress this semester. You should be fun this semester. You will get an A in this class if you're an active member of the class. If you're part of your team, if every week your team puts in a good faith effort and makes a lot of progress towards getting that lab to work as you would hope, you're going to get an A in this class. My goal is to get a 4.0 GPA in this class. I say that in CPRE 381, and I don't really mean it because it never really happens. But in this class, I actually do mean it. I expect this class and everyone in this class who comes each week, who participates with their team, and puts in a good faith effort on the MP assignments, I intend to give you all A's. I don't have a lot of bandwidth or TA hours for grading, and I just want to get grading to be kind of a side effect of all the fun work you're already doing. And then separately, of course, my goal is really to inspire you or motivate you to do more, to learn more. After this class is over, I think it would be an excellent outcome if you realize as a team or just individually, boy, I would love to do more. I would love to take this approach and now also implement something else, or explore this other class of algorithms, or do more FPGA design or more CUDA programming or any sort of things. I know quite a few of you, I think just by the nature of who signs up for a class like this, are considering or have considered or are already in concurrent BS master's programs. This could be a great source potentially of MS project ideas. And if that's something you're interested in, we can wait till we get a little bit further along in the semester. Let's wait till about week 6 of the semester before we start discussing those. But that would be absolutely a great opportunity. Um, I tend to, have more students who are interested in working on projects than I have good ideas to kind of share with you. So if this inspires you to do a master's project based on that, sign me up. I'm happy to help out and advise that project. Okay, so no more syllabus items, I believe, at least for now. Um, so this is we're going to do a little bit of graphics history here. I'll be honest. I feel like I'm not necessarily doing my job in a class like this if I don't at least provide some of computing graphics history. Those of you who've taken other graphics courses, and there are a handful of you may have seen some version of that. Again, as with everything, my focus and my interest is on the architecture side of things. So in the very beginning, this was very much an analog topic. As with much early computing, certainly for this, the earliest computer-driven graphics were really just oscilloscope apps or ways of adapting an oscilloscope to be able to render what we would now call vector graphics or things on vector displays. Um, so people actually manipulating the actual analog electronics of an oscilloscopes to generate either waveform artworks or actually to build some sort of user interface showing that you can actually draw shapes in an interactive fashion on what was effectively a hot wired oscilloscope. That's the sketchpad system on the right from 1963, and it's pretty fundamental to computer graphics. That initial approach of kind of building what we would think of today as a very basic kind of image editor or paint based editor, but being done back then before we really had fully programmable uh, uh, computing systems of the type we take for granted today, is what makes it a very amazing and fundamental accomplishment. Um, Depending on our time today, I have a few videos for each of these little stages as we look at the various generations of architecture. I have the sound turned off, but I don't think none of them for any of them the sound is absolutely necessary. So this is actually a video interview, and you can find this if you're interested in seeing it in more detail. This is Ivan Sutherland actually displaying that initial sketchpad system. So can everyone see that? Okay. I mean, it's a YouTube stream on my monitor, then being passed over Zoom. I can share the actual links for these if you just want to watch them, but you can also probably find it yourself just by looking it up. Okay, thanks, Isaac. Um, so this is Ivan Sutherland talking about, he's in his MIT lab, what would now be not Lincoln Labs, but their other major lab whose name I'm drawing, the CSAIL lab is what it would be called now, um, showing that using basically a magnetic pen and using that to kind of store information in memory, he's able to do. You can call it very rudimentary, but this is before we really had anything in place, and so at different settings, so that I'm going to draw now. This is my circle arc view of drawing sort of things, and from the perspective of maybe early CAD, this is an incredible accomplishment. So this is Sketchpad. This is sort of the very early days of, we can call it computer graphics, right? This is a computing system that is generating graphical output. So this is absolutely generation zero of computer graphics. Generation one, and okay, when I mention these generations, this is kind of my opinion. There's no obvious, everyone gets together and decides that this is a new generation. It is a continual evolution, but along the way, there are significant hardware and software milestones, and so and significant demo milestones as well. So if we call this generation one, you could also think of this as the first availability of workstation class graphics hardware. What we would now consider not a GPU, that term didn't really exist back then. But if you're familiar with SGI or Silicon Graphics, their big accomplishment, their real initial intellectual property was basically just floating point multiplication, addition, and division that they could do in hardware. So by building a special FPU, essentially, they were able to accelerate, the kind of things that we now kind of take for granted. And also on the software side, they were designing and inventing what is now known as OpenGL for their API for doing computer graphics. But certainly, what was capable, certainly in real time, was relatively basic by today's standards. Wireframe models were a very popular demo in that generation one. Relatively simple, color interpolation, basic, very simple rasterizers were possible. Um, but that SGI and that initial hardware workstations, that was their big accomplishment, was VLSI hardware accelerators specifically for doing computer graphics. On the software side, this was also where you start to see, the Reyes renderer, now kind of evolved into what's still referred to as RenderMan today, being able to do um, relatively realistic looking lighting of scenes, not in real time, but being able to do so even with the software infrastructure to handle that in an offline manner. That was the Reyes renderer. So those are all the folks who joined what became Lucasfilms, and then eventually joined and created Pixar and all that. And it's all really starting back then from initial algorithms and software research in the late 1970s to the first hardware and then corresponding software platforms in the very early 1980s. Demo wise, there's a million things I could show for that era. I've always liked this one. I can't say it's the first or it's the best, but this is certainly from a TV show in 1985 showing what was possible in back then called Reyes, now sort of Renderman software back then. So this is obviously it's not real time. This is for a television show. This is showing the stained glass night, showing that what could actually be rendered with actual realistic looking lighting effects. Intentionally, it's a model that's not meant to look three dimensional, so it's kind of a funny little artistic choice here as well. But that was what was possible back then. And before that, if you looked at effects, they were almost all physical effects drawn onto film versus computer generated effects. So this is, I don't know how gory this scene gets. This is probably not so much. This is a computer generated effect. This scene here, that's 1985. That was what was possible with RenderMan back in 1985. Just referring to that, we'll refer to that as generation one here. Generation two, more of an evolution than necessarily a revolution. But what really became possible then in that generation was you could have at your desk an SGI workstation that had a frame buffer hardware, had enough memory storage to handle rendering not pixel by pixel, but rendering into an entire buffer at a given time. And that allows for all sorts of techniques that we now also very much take for granted, which is you can have your shaded and per vertex lighting. You get that kind of flat effect, and it also allowed for hardware support for three-dimensional things using depth buffers and things of that nature. This is a little bit of a misleading. This is the Utah teapot model that we have here. This is a slightly misleading thing. From any given generation, there are a lot of different figures I could have chosen. There's a pretty famous benchmark from the University of Utah computer graphics group from the 1970s, and we still kind of use teapots. You may see them in various demo scenes that benchmarks that are being shown. But this is showing something that's been flat shaded. So each vertex, and we'll talk all about this when the time comes, each vertex gets its own light calculated. Then we interpolate that across the individual triangles. It does allow it to look relatively three-dimensional, but you can really see the artifact of, you can actually kind of see each triangle in that model, even though it's lit in a three-dimensional way. This generation two, very much the era of SGI, a company that kind of only exists really in name or via some patents today, was very much the premier company for computer graphics in that era. And I love, although this would have been great to have the sound, because you have to take my word for it. It's got kind of that 1980s infomercial sound going on right now as I'm playing this. This is a SGI kind of demo tape from 1990-ish, I guess. And this is SGI showing what their hardware is able to do. Um, with these demos, I was kind of getting to this point a second ago. It's not always that clear, is it demoing the hardware? Is it demoing the artistic ability? It's always a combination of both, right? But in this case, this is showing what that SGI workstation hardware was capable of doing, let's say in 1989 or so. If you had one of these at your desk, you were a very valued employee at your company, and maybe your company owned one or two, depending on what they were doing. But this is showing the different things that you could render for commercials and film and for CAD tools and things like that with your SGI workstations, let's say in 1989. This is unfortunately 10 minutes long. I'm not going to play the whole thing, but it's really cool to show this is SGI showing off what they were capable of doing with their graphics hardware back then. In the interest of time, I'll have to pause it, which is unfortunate. I love for us to just sit through the whole thing. So I mentioned the milestones along the way, and YouTube time is over for the brief time being here. A big aspect of that was workstations that had that hardware frame buffer, and I've used that term a couple times now, and I haven't defined it properly. When we refer to a frame buffer, referring to this idea that you can store the information associated with what you want to render in the screen in memory. The term you may hear is as compared to vector graphics, where everything has a positional description that is directly drawn. In raster graphics, we have an array, the so-called raster. You could think of it as a two-dimensional matrix if you wanted to, of picture elements or pixels that we want to store in the frame buffer. It is a buffer that allows us to store what is to be rendered in a given frame. So for a given resolution, if you have a 640 by 480 resolution, you would have some amount of storage that's a multiple of 640 by 480 in that SGI workstation that you had there. That would be our actual memory. That's our actual frame buffer memory. That's what allowed hardware to progress beyond drawing vector graphics and showing just very basic outlines and wireframe images to actual these filled polygons, because for every element that you wanted to render, you had a place to store it, to read and write from it in memory and manipulate those values in memory. And so when we refer to pixels, and later on we'll have to be a little bit more precise with our terminology, we're referring to, at least now, from the systems perspective, there's a mathematical definition of it as well, but from the systems perspective, we're referring to that location in memory that's going to correspond to what we want displayed at that equivalent XY location on our screen. So anyone who's ever zoomed into an image know you can see that, right? As you look at something that, because of its resolution, looks like a very obvious, contiguous, kind of analog-looking thing here. For something that's stored as a digital image, you zoom in enough, and you can see the individual pixels there. That what looks to be gray, or what looks to be, multiple colors here, is really just the gradients as we zoom in, and each of those individual, be a little careful with the term, but each of those individual little squares, don't tell people I told you that pixels were little squares, but um, each of those little squares is corresponding to one location in our frame buffer. And so that was a big accomplishment. It was really just waiting for memory technology to advance to the point where such a thing was even possible, that you had enough memory to store reasonable sized images and be able to access them fast enough, separate potentially from all of the rest of memory that your system would need to be able to run the software for that system. So when we talk about frame buffers, we kind of take them for granted. I think in our existing, you spec out a card and you say, well, it's got 4 gigabytes of GPU memory. That seems good enough for me. But that certainly wasn't the case. When we think about these early systems and what was really possible, and here I'm going even back, to pre SGI hardware here. Uh, Being able to store things in a frame buffer was the most significant expense of those systems. That picture there is a very early kind of interactive painting application, the Super Paint system. You could purchase such a thing as an actual product, and just to be able to store those simple 8 bits per pixel at somewhat VGA-ish resolutions, that was a $12,000 machine. That's in 1972 dollars. So that's a very expensive piece of hardware today, or equivalent to a very expensive piece of hardware today. We tend to take it for granted, I think. That frame buffer, we have enough memory to do what we want to do. You will see, though, that as we're working on our labs this semester, as you're building your own GPU, we really can't take it for granted anymore. We potentially have enough physical memory. We have enough bits of storage in our memory on the FPGA platform that we're using, but can we access it fast enough? So it's not just a storage requirement, it's a throughput or a bandwidth limitation as well. I wanted everyone to just take a minute here and consider this sort of mental exercise here. you may need a piece of paper, or consider opening up a Windows calculator or something for this one. So nowadays, if we think about a 4K style display, which we kind of take for granted, right? That we can support 4K, and of course we take for granted we can support multiple 4K monitors. But let's say just a single 4K monitor, where that's referring to an actual physical resolution, right? We have uh, 2,160 rows of pixels times 3,840 columns of our pixels, and we also assume there's a refresh rate of that display. We haven't talked about refresh rate yet, but thank you, Braden. But we are referring to, how many times should we be able to expect to get a new image off that display for something new to come in? And the math there is something, it's really just multiplying it out. But the actual bandwidth in terms of it is pretty significant. And not just the individual bandwidth, if we think of it just in terms of the individual latency, on average, how much time do we have to grab a single pixel? I think both of those are going to kind of be impressive numbers here. So let's just take a minute. I appreciate it, Braden. You got started on the pixels per second calculation here. But what about the actual time? What time would it require on average to read a single pixel from memory? Just take a moment and think about it. Work out the math on a piece of paper that you have handy, um, or you can use a calculator or something for this. I am also going to open up a calculator because I don't have the answer in front of me. Okay, let's just take just a moment here. I appreciate, Micah, Braden. It's always fine to answer in the chat here, and I appreciate that. Um, this is just a thought exercise of what does it take to drive a 4K display. In practice, there's all sorts of techniques that can improve upon sort of the naive assumptions of how we're going to go about driving a 4K display. But ultimately, that 4K display means you have uh, that many pixels, roughly 4,000 times 2,000 pixels. So you have roughly 8 million pixels, and you're wanting roughly, right? And you're wanting to push them at, let's say, 120 frames per second, or you want to push new images 120 times per second. That is roughly 1 billion pixels per second you'd want to push out of that memory and to a display. Right? That's the rough order of magnitude math. You can get the exact number, and that's fine as well. All I did was just multiply those three numbers, right? 3840 times 2160 times 120. That's how many pixels I want to, and not just display, that's how many pixels I want to be able to render, ideally, right? So it's not just a read speed, it's both reading and writing. And we many of you may know that in modern graphics application, it's not a one-time thing. You don't just write one pixel once and you're done with that pixel. You're doing multiple passes, and all sorts of other reads happen to be able to draw that pixel appropriately. That's 1 billion pixels per second just in the sort of best case scenario here. So that answer of 1 nanosecond per pixel is also saying we just kind of invert that value. That's extremely fast, right? That's a 1 gigahertz clock dedicated just to reading that individual pixel out at a time. So frame buffers are something we take for granted, but I think as we start to design our systems and we recognize these fundamental bandwidth calculations and also potentially latency calculations as well here, and then now as we're designing the hardware ourselves, we're going to recognize that that's the case. I think that so much of what we are doing architecturally is to try to take as best advantage as possible of the bandwidth that we have available in our system. And I'll talk more about this in a minute. So keep those kind of numbers in mind. When designing the labs for this class, I had to decide, what frame rate or what resolution would be appropriate for the GPUs that you're designing. And we're doing 1080p resolution. I can't really justify it other than I thought, well, it's the year 2021. We should have at least, high definition GPUs that we're using in this class. But that has big implications on, of course, again, how much storage you have, as well as how much bandwidth you need out of your memory. So there's some follow up questions which I think are great in terms of, I said, state any simplifying assumptions you make. I was referred to it in terms of pixels. So in terms of pixels per second or nanoseconds per pixel, we can answer that question. Now, in terms of what does that mean in terms of gigabits per second, now we have to then calculate, well, how big is each pixel? We'll talk more about that next week. But yes, it could be 8 bits, it could be 1 bit, of course, it could be 8 bits, it could be 32 bits. There's all sorts of different pixel resolutions that what system can support. For our labs, we're doing 4 bytes per pixel at 1080p, so we could do the equivalent calculation for how much bandwidth we need out of our off-chip memory. Seeing the other question, there's a question about prefetching. Prefetching is a good thing to think about. When we're building these systems, the more relevant term for our purposes is DMA. So when you're wanting to display what you have on your screen, and we will definitely talk about that next week, we don't even want to concern the CPU or the computing side of things at all with regards to that transaction. It's kind of an automatic thing, right? Every 1/120th of a second, we need to spit out that 4K image and make sure it gets displayed on your screen at the end. Yeah, and it could be more than it could be 30 bits per pixel. Absolutely right. Um, and we would tend to have dedicated hardware whose only task is to take care of that. So as you will see eventually when we get to the MP1 infrastructure, there's a lot of that hardware on our chip dedicated to leaving the CPU alone, leaving your GPU alone. Its job is to DMA, do direct memory access, grab whole buffers at a time, and connect them to our video out on those boards. Um, it is a type of prefetching in a sense, but prefetching usually refers to a pipeline or a processing architecture grabbing those values in advance. This is a dedicated circuit whose only job is to copy large blocks of data at a time. Let's continue down our path, our historical path here. Um, Maybe over time, my beard will get a little bit more gray, and I could stroke a nice gray beard, and talk about back in the old days, etc. Anyway, Generation 3. Refers to a lot of additional kind of incremental improvements over what is possible with what we now refer to as fixed function hardware. So these were highly configurable graphics accelerators, but they weren't in any shape programmable in the way we now think of that term. But still, because of what was just continued evolution in terms of the amount of memory storage and bandwidth and just the amount of transistors we could dedicate to a piece of graphics hardware, you were continuing to see impressive visual effects that became possible. So I talk about texture mapping and per fragment texture hardware being part of that third generation. We will definitely talk about texture mapping this semester, but we're really referring to you can think of it as that wrapping paper type of effect. I have usually a two-dimensional image, and I want to wrap that around potentially a three-dimensional shape, and that's what allows you to get all sorts of things that you can't otherwise easily describe using just geometry itself. So this is the same Utah teapot. This has got, I believe it's two different textures applied to it here, and you're kind of saying, well, you can make it look like basically whatever you want. If you could generate a texture either offline or online, you can generate a texture. With this hardware starting in Generation 3, you then had dedicated units that would allow you to apply that texture. It's not that complicated. We'll do it in class, in lab. It's grabbing the value from the right location in memory and setting my pixel to be that location, to be that value. But then you can apply all sorts of fun little visual effects with that per fragment texture hardware. What I was thinking of the right demo for that generation. This is the original Quake One, uh, running kind of mediocrely on an MS DOS home computer back then. So probably not running with much of any, based on the resolution this person's running it at. Probably not much of any hardware support and running entirely in software. But I don't know that for a fact based on this somewhat random demo here. My goal for our labs this semester is to be able to run something actually a little bit better looking than that by the end of the semester. The only limitation I have right now is not the capabilities of the hardware you are building. You'll have no problem being able to do most of what's in that particular scene. We got to find the right software code base to be able to port to our hardware, and I haven't found that yet for this semester's class. We have time. We have time to find that. But texture mapping becomes fundamental. There's only so much you can draw with just geometry, and you wind up with demos that look like this or like this, right? That's what you can do with just pure geometry. When you want things to have more not that this is necessarily a realistic looking thing, but when you want things to have more variety in terms of how they look, more realistic in terms of what type of things are available in nature and in things we can make ourselves. That's where texture mapping becomes fundamental. Now we talk about generation four, and that's a pretty big milestone in terms of having what's referred to as programmable pipelines. So now we have hardware for which we can write programs for the GPU itself that allows us to determine what transformations we want to apply. And so it's programmable vertex transformations and programmable fragment transformations. This is really where the term GPU really started. It's not a term that's as old as computer graphics. It was originally more of a marketing term, now it's become a very ubiquitous term to refer to graphics hardware. But that refers to the programmability of our graphics hardware, that term GPU. And that's really, that era of 2000, at least as it was available for regular old users to purchase and use in their own personal computers. Um, and you're starting to see the era of just a couple of companies really starting to dominate the market, and that's really still where we are today in terms of what graphics technology dominates the market. Really, just three companies at this point have interesting GPU designs that we use for commercial hardware here. This is not necessarily that interesting of a picture here, but this is again the teapot, showing what is also just possible once you start to have programmable transformations. It's a little misleading. You could have done that with the previous generation just by generating the texture offline. The difference is it's something that can be generated online here, where something in your fragment shader is showing a little bit of a noise effect, and having programmable noise shaders was a very big thing, back in 2000. A little bit of reflection effects happening here as well. Once you have programmability, you still have computing limitations, but really it's an artistic limitation. Given the computing limitations, what mathematics or what artistic vision can I have to be able to describe what I want in my particular scene here? So when we start to definitely look at those demos from that era, um, well, this is showing would be offline rendering. If you haven't seen Wally, that's also your homework for this evening. I assume of your generation, you've all seen it, but if you haven't, this is probably Pixar at its peak. Okay, that's also just my opinion. That's not fact. Um, Showing what's possible with RenderMan now between the young Indiana Jones scene with the stained glass knight in 1985 to now 2008. What's possible using basically an evolution of the same software, just running on probably a lot more hardware and a lot more capable hardware then. And now, really, when I refer to things as being artistically limited, that's not a negative thing. It's now up to the artist's vision of what we can either generate enough artistic resources for, or it can be visualized for what we want to be able to render both online and offline. With programmability of our GPUs, that's the fundamental limit. That's your homework if you have not seen that yet. Although nowadays I couldn't even tell you where to find it. Which streaming service has it? Probably Disney Plus. So uh, share your Disney Plus account with the class, and then we can all watch it this evening. Um, we've moved past that. It's maybe more of an evolution than another revolution past then. But Generation Five, to me, I refer to the first creation of unified shader architectures. It's a very similar thing, and some of that, in fact, is actually marketing. But the main distinction is in the previous generation, we have programs that we write to manipulate vertices, and then separate programs we write to manipulate fragments. And we actually do have to separate them. There was hardware limitations that said you can write a vertex shader in a certain way, and you can write a fragment shader in a separate way. And that limitation does go away in this Generation 5, where you just have a core. You have a shader core in your GPU, and different companies refer to those as slightly different things, but they're all very similar looking. And you have arbitrary programs that you can now write. You could still write code that looks extremely similar to the previous generation, but now you have even more freedom that whatever your computational limitations are on that device and your bandwidth limitations on that device, you can write code that can execute on that particular device. So I refer to sort of arbitrary parallel programs. This is also the emergence of GPUs, not just as a tool for doing computer graphics and doing rendering, but also GPUs now for doing computation. There was an inkling of that in that 2000 to 2009 era, and people were kind of kind of tricking the GPU into doing general purpose computation, and we will get a chance to talk about that this semester. And then in this generation, the recognition that we do have a lot of floating point hardware on these devices now. These are little high performance computers on a chip. We should start using them for that purpose, and that has become a very prominent use case for graphics hardware today. A couple questions I see in the chat. Yeah, a couple very similar questions. I appreciate it. So, will our GPUs, so the ones we are designing lab, will they be controlled or will they be more like co-processors? Um, Almost all GPUs are still co-processors. Almost all. It is there's some fundamental limitations of what GPU architecture supports and doesn't support. Even if it's a very tiny CPU, there's always a CPU somewhere on the system to handle some of the mundane uh, interfacing with operating system and system software and things like that. Things that the architecture has not evolved to necessarily be good at. So ours is no different. We have a couple different CPUs in the system. On the actual FPGA board, I've left a small embedded microprocessor core just in case we need it. Right now, we're not using it, but it's there and it's hooked up to everything. And you could write code and interface with the entire rest of the system via that little core there. And then this FPGA board is configured basically in a co-processor way, in which the workstations that you're connecting to, that Xilinx dash 1 through dash 8, that is what's running our driver code. That is the CPU, and that is then sending commands over the bus to the GPU implemented on that Nexus Video FPGA board. That's not really a compromise. That's kind of the right way to do it. That's still sort of the standard way that we do CPU GPU interfacing. What is different is instead of using PCI Express or something like that, we're using Gigabit Ethernet for that interface. That was a compromise in terms of something I could get working on that particular board that didn't require custom Linux driver support and didn't require us to reboot the machine every time we changed something in hardware. But it is a relatively realistic simulation of what a real GPU CPU interface would be here. One more question we have. We'll recreate Wally on the GPU. Probably not. But will we get to the evolution of general cores? Well, today we're talking about it, so that is what is there. We will talk about it in detail. What does that mean in practice as we've evolved our GPU over time here? This is meant to uh, motivate you a little bit. This is not something to memorize or anything like that. This is just my take on where we've been and where we're going in terms of GPU technology. So uh, don't stress out too much about it either. So that evolution is continuing. This teapot here is showing how maybe you're doing something of an environment map. Again, one could still have done that with older technology. Anything you can render to a texture, you can render to a texture offline and then map. But the idea is that in this generation now, in theory, you could do that in a real-time manner, such that you can look at what the rest of the scene is trying to render that to a texture, showing this kind of camera effect here, and then render that to the actual teapot here in real time. That's what allows you to get more realistic looking scenes, right? Once you have things that reflect off each other, not realistically reflecting, but we're kind of emulating that reflection effect, you can get much more realistic looking scenes in that sense. So now I would argue that we're now in generation 6, not been a massive break from what was previously available. Oftentimes, just more of the same good thing is what I would describe as what's happening today. Definitely algorithmically in terms of what software capabilities have caught up. There's definitely been an evolution of what is possible for illuminating scenes and having more realistic light models in our scene. And then on the hardware side, we are also definitely seeing support specifically for that class of algorithms that we're going to push to the very end of this semester. You can refer to them as more physically based rendering. You can refer to them as ray tracing if you want to, or you can refer to it as global illumination. Trying to more accurately model light as it propagates into a scene allows you to get really cool effects like this teapot here, right? Which is showing that, there's a bunch of glass marbles inside a glass teapot. That is a very hard thing to do with just traditional programmable texture mapping on that particular surface, because it's assuming then that there's a light source in that scene and that light is reflecting and refracting through all the various marbles, whether it truly is or not. That's what those kind of algorithms allow you to do. And hardware has been evolving then to recognize that as a different class of graphics computation that's needed, and to start adding that kind of features to your chip. So if any of you have an NVIDIA RTX of any way, shape, or form, you have some sort of support for doing real-time ray tracing on your particular device there. It's a good chunk of its marketing, but we're moving in that direction. That much is very clear. And likewise, certainly those of you who've taken CPRE 482X in the fall, you had a whole semester on that, right? Commodity hardware evolving to support real-time machine learning, accelerating inference and neural networks. It turns out to be mostly all the same hardware. There isn't a huge difference between the type of math we do to calculate ray object intersection or transform a vertex from one view coordinates to another set of coordinate system. It's all basically the same math. It's all matrices, it's all vectors, it's all matrix vector multiplication. So your MP0 is a toy assignment, but it is a fundamental operation that we see time and time again. So we'll see how all this shakes out. Ask me again in 2 years and see where this evolution of hardware leads to. Every time NVIDIA makes a new announcement, it is partially marketing and partially something interesting that's happening there. Um, Matt asking what hardware ray tracing really is. Yeah, intersection testing though is a big part of it. So there's some hardware accelerated data structures for doing ray tracing, um, but intersection testing is also just matrix vector math as well, right? So there's nothing that new under the sun. It's part evolution, part branding as well. Certainly, there's no doubt that just given the continued scaling of VLSI technology, what is possible? I think I skipped a generation here. What is possible with modeling light has definitely changed over time. So this is 2012 Jensen Huang keynote, and he always likes to give fun little tech demos during his keynote. And some of them are real, some of them are pretending to be real, and they're actually not in real time. But they're all really cool, showing what was most certainly, I would say, not possible in previous generations, to get that kind of glass effect and to show that for a given light source, this piece of glass is this much more bright than this other piece of shattered glass. That does require some sort of light model in your scene that requires a different approach. Doesn't map well to traditional programmable graphics hardware, and so new hardware is needed to do that. Finally, if we look at the relatively recent RTX demo, um, I'll mention it one more time. I think oftentimes it's the artistic vision that matters as much as the technology here. You could give me the most expensive hardware in the world, and I wouldn't be able to come up with anything approaching this type of demo, right? Because that requires a Pixar style artistic vision that you would then use your hardware to render and model. We're getting to the point where we can start to model what is maybe indistinguishable from reality in terms of what computer graphics is able to provide for us. There's no doubt that these demos are all full of shiny marbles, and they have been for about 10 years now, because that just seems to be something that we can model relatively easily. Sphere light intersections is a very well understood problem, and the math isn't very hard for it. Um, we don't often in real world have, you know, rooms full of shiny marbles that we're interested in rendering, but it makes for really cool tech demos. We have definitely seen, even just through a continual evolution of hardware capability, the ability to generate scenes like this, which would have really been unheard of even 8 or 9 years ago. Um, we're going to learn some of these techniques. Now, I would also add, and this is very mesmerizing, I know. I'll stop it then. Um, I should also add that in terms of our hardware target in the lab, what I had to really balance was more of what is possible for a now 14-week semester with teams of 3 and teams of 4 working on something, right? What is possible with the FPGA platforms that we could purchase at a reasonable price, and you would have enough time to be able to learn how to use and to master this semester. Um, so we have to make compromises. And if I had to say which generation we're designing for, it's not that one. It's probably early generation 4, mid generation 4 is what we're targeting in this class. Um, that's still quite a bit, because a lot of the rest is just evolution of programmability, adding more programmable stages to the pipeline, some additional hardware accelerators. We're just limited by the practicality of this being an undergraduate course. NVIDIA is a $20 billion company, and I'm not worth nearly that much. I'm getting there. Give me time. I've really invested a lot in GameStop lately, um, but it's still a really realistic GPU that we are creating this semester. So I want you to keep that in mind as you're struggling at parts during these lab experiences. This is about as good of an outcome as we could possibly hope for. We're still limited by artistic vision more than anything else. The shader code for this is not trivial at all. We should be able to effectively support that by the end of the semester. But having said that, there's a lot of fun in just getting this to work, and that'll take us a few weeks this semester. And we're gonna build our way up by adding functionality as we go. You don't have to humor me by laughing at my humor. That's not part of your class participation. My poor attempts at jokes. That's not part of your class participation score this semester. But I appreciate that. And I also talk about video game consoles. To the extent that those are really an interesting separate case. That definitely used to be the case. There was definitely a pretty big split between what I'll call it workstation class hardware was capable of versus what something you'd buy at GameStop would be capable of. It's really not the case anymore, and arguably, video game consoles aren't really interesting anymore. They're cool, and they can really play wonderful games, and they're using relatively cutting edge technology. They're not all that interesting from an architecture perspective as compared to what you could also just buy for your workstation class hardware. But that was definitely not the case in the beginning. In the very beginning of the original consoles, they all had their own custom. The terminology they use would depend on what console you're talking about, but digital signal processors or picture processing units, or they would even call them GPUs. And they were very custom, and the companies themselves would be manufacturing their own chips or closely contracting to manufacture their own chips. Um, and that's its own separate kind of cool walkthrough. We could absolutely have had a class where we're building various generations of from Atari to NES to Super Nintendo. We probably couldn't get any further than that, and do that kind of hardware. Um, it's doing, when you're focusing it primarily on 2D graphics, at least in those generations, it's a completely different set of techniques one would have to learn and have to apply. But since then, and I don't know exactly what year I would say, they've stopped becoming interesting. I guess after the PlayStation 3 generation and beyond, they're really just workstations with maybe some clever sub optimizations happening architecturally. What has made them capable of really rendering very cool effects is the fact that they're sort of a fixed platform. You purchase your Xbox and you can expect it to be supported for 7 or 8 years, and so game companies can really focus on those low level optimizations and artistic techniques that scale well to that particular hardware that allow you for maybe better looking effects than what something hitting a lower common denominator would be able to target there at the end. But nowadays, if you do purchase your Xbox Series X, it is a very nice piece of hardware. The GPU in there isn't all that interesting when compared to what you could just buy for your laptop or your workstation. Finally, let's get back to where we were here. You know, again, just as our introduction, as our motivating talk this week. So, what does graphics hardware look like? So, this is a class, and you want to know more. And I know I can tell, and I love it that you want to know more right now. Okay, let's get there. So, what does graphics hardware look like? Well, there you go. That's what it looks like. Done. Class over. Haha, just kidding. No, actually, it looks like that. Haha, just kidding. Okay, so die photos are not very useful for understanding graphics hardware. They tend not to be released that much anymore in the first place. Um, I believe that's a GP1. That's a Pascal class hardware from NVIDIA. So that's a relatively recent die photo they have there. When we talk about what graphics hardware looks like, what we're really referring to are the stages corresponding to the various aspects of a rendering task. So when we talk about what does hardware look like in for a CPU architecturally, we tend to be referring to, um, amongst other things, what does our micro architectural pipeline look like? How do I get from fetching an instruction to executing an instruction and every step along the way there, right? That's CPRE 381. If we had a 481, that's what that course would cover. That's 581. That's micro architecture. On the graphics side, and taken all that I said about the evolution into account, there's a lot of different things and a lot of different variants there. We still tend to define our graphics architecture and graphics hardware based on how they do implementation of the fundamental steps of the rendering of the traditional rendering task. And even when we look at RTX improvements and hardware support for machine learning and things like that, the vast majority of those chips are still dedicated to how do I go from input geometry to an output display at the end of the day. And that's what we're going to cover when we talk about that topic three of our graphics hardware pipeline. And as we cover these various topics here, um, we start with geometry. So we start with vertices describing positions of a triangle. And it's almost always triangle. It doesn't have to be. And those of you who know more know that we can describe other surfaces and have custom hardware to generate triangles for us. There's a lot of things going on there. But we start with triangles. We'll talk about why we start with triangles. It's partially for historical reasons, but also partially because the math works out really well for triangles. And then a good chunk of our hardware is dedicated to this task of rasterization. Now, I use the term raster for raster display and raster graphics. They're all related. You maybe have heard the term raster scan before. They're all interrelated terms. From the perspective of this flow from left to right on the slide here, rasterization refers to filling in the triangle. What we know we have a triangle, what should go inside that triangle, and why. And that is MP2. That's the hardest lab this semester, I think. But it's a fun one too. How do we build hardware that, given a triangle, tells me what's inside that triangle? And we will cover that in depth, and you'll have a lot of fun building that. Then there's a texturing phase. We talked a little bit about texturing, what that means. What is that wrapping paper we want to apply to our individual triangles? There's a lot of configurability and now a lot of programmability associated with that phase. We'll be implementing a relatively straightforward approach to that because there's a lot of different options and we have to kind of limit what we would want to be able to support. Then we have the fragment processing. Now that we know we have this triangle and this triangle had a texture applied to it, how does this relate to the rest of the triangles in our scene? It's okay if you don't get that yet. We don't have to get that yet. But for example, in this very simplified view of things here, we go from our triangle and we realize that we actually, because of how we're modeling a three-dimensional object, we actually only want to display part of that triangle. And part of that triangle is blocked by something that's actually closer to the camera in our scene than where that triangle is. And then finally, we have our display. So from our frame buffers, we actually have to display something out on a display screen here. A couple questions coming in about it. I love it. How does ray tracing fit into all of this? It has its equivalent set of software stages, some of which can be mapped to these programmable hardware that we'll have available to us here. But outside of sort of academic work, there are no real ray tracing hardware pipelines that look in this fashion. They do exist in academia. There's not enough need for a commercial product that only can do ray tracing. It can't do this type of rendering as well. Because what you'll see is oftentimes you have to kind of blend both approaches. It's not really one or the other. I'm talking a little out of school here. So that's the rendering pipeline. So that term pipeline becomes a little bit overloaded as we start to use it this semester. You're familiar with 381 or ComSci 321 style processor pipeline. That term is still valid. Pipeline, stuff flowing through. Remember the laundry analogy from your textbook, right? That's still a valid use of the word pipeline here. We then refer to the term the graphics pipeline. That is both a software pipeline and a hardware pipeline. But this diagram GRF or GRTFD here is a software. It's a rendering pipeline. This could be implemented entirely in software with no hardware support whatsoever. And you have different types of rendering pipelines that are available. This is a very traditional generation 2, rendering pipeline here. And then each of those individual stages for the particular piece of hardware we're interested in exploring or designing would take each of these rendering stages, and each of them would correspond to potentially multiple and potentially programmable hardware pipeline stages. We go back to generation 1, which is just entirely fixed function hardware. If you had taken CPRE 480 in spring of 2012, that's the version of the hardware you would have built in that class. And you have this same kind of flow diagram. I think this slide hasn't really changed much since then. But that would correspond to one very deep VHDL pipeline. There was no programmability along the way. And ultimately, each of those stages would have as many hardware pipeline stages as you would need. And they would all be kind of interconnected together. And so data comes in, pixel comes out, large number of cycles in between. And that's what modern hardware looked like from that generation. Now there's still a lot of that. Now, even in the most programmable advanced hardware that you can purchase, you still have to do hardware pipeline for rasterization. That is not a software programmable component in any GPU that I'm aware of. So that part that we're building for MP2 this semester is still very much valid. It hasn't changed. There's maybe more of them. They maybe have a couple more configurable tweaks to them. Maybe some early optimizations are possible. The hardware hasn't really changed otherwise. But then also now you have these other stages that some or all of them are software programmable as well. So that term pipeline becomes really overloaded. We have rendering pipeline, we have digital logic pipelines, and then because we have these programmable shader cores in our GPU, we have programmable hardware microarchitectural pipelines as well. And all those terms are valid. We sometimes just have to be a little bit more precise with how we're using that term and what context we're using them. We will see as we talk a little bit about graphic shader pipelines, a lot of that 381 style stuff doesn't apply by design, not accidentally, that in order to limit the headaches associated with supporting really deep scalar pipelines, the solution has been to not support those and to have really vanilla boring pipelines and to make up for it by having a lot of them. So in some sense, the microarchitecture we'll talk about this semester is easier to implement than the 381 equivalent. The difference is really the scale, and then of course the difference is all these other things that are a completely different type of pipeline than what you had learned in a 381 type class. We're jumping over a little all over the place a little bit, and I don't want to. My goal is not to overwhelm you today. When I refer to modern graphics hardware, we're generally referring to what's referred to now as graphics processing units or GPUs. Those are parallel hardware implementations of some version of that rendering pipeline with a lot of new fun tweaks, added in. Deep, very deep, very floating point heavy pipelines with very large transistor counts, relatively small amounts of cache. That has also been changing a little bit over time. But really, the dedicated usage of the transistor budget for your GPUs is how many of those floating point units can you fit on a chip, and can you keep them all fed? Can you keep them all with data coming in with throughputs and compute rates that are kind of mind-boggling to me? Maybe when you just think of them as numbers on a page, it doesn't mean all that much. But when you compare that to what was possible even 10 years ago, it's a little mind-boggling that hundreds of billions of pixels per second are very much possible in modern graphics hardware. And then with modern graphics hardware, with programmable shaders in most of those stages, but not all of those stages of the pipeline. And some of you may remember this term from your previous architecture class, almost all of them with some sort of SIMD mode of operation, where for a single instruction, baked into the instruction set itself is some sort of parallelism inside that instruction. We are not just going to want to do one addition per instruction. We're going to want to do 4 or 8 or 16 additions for that given instruction. Some of you may have explored a little bit of that in, let's say, CPRE 381. It wasn't necessarily a required aspect to explore. It depends on when you took the course and how much you dug into those topics. We'll get a chance to dig back into those topics. It's a relatively straightforward thing, but we do have to explore it and make sure we understand how to build a SIMD processor. And then with more and more, general purpose computation being the case, that NVIDIA, for example, shows a different architectural diagram for their compute path versus their graphics rendering path. It's the same exact transistors. It's really more of a programming model difference than it is an architectural difference between the two, at least today. So when we talk about that programmable hardware, we have our first unified shader architecture. And I think because it was the first, at least from NVIDIA, it's still the best documented one of all the various designs they've had. The Tesla class hardware through the ages. So this is your G80 chip that you have here. And there's a lot going on that you don't need to know right now. But it's attempting to show And if you squint your eyes, maybe you can see that previous diagram of the rendering pipeline. Maybe, maybe not. From geometry to display, it's still here, but it's not as obvious that's the case. First off, this diagram is more of a top-down diagram. So from geometry means in this case, um, from that host interface, so from the CPU side, sending me my geometry, sending me my vertices. I'm now going to, my task is now more of how do I create threads and workloads for these individual programmable processors that we have here. S- we don't need to explore this entire diagram right now, but some of those things should look vaguely familiar to you at least. Okay, L1, that's what we're going to refer to it, L1 data cache, L2 cache. We have our programmable cores here, and as we go from geometry, we eventually get through to our display. That's not really being shown in this diagram, but that's what that frame buffer is meant to indicate here, that here we are connecting this to finally our display at the end of the rendering process. It's a lot, and we certainly can't build something at this scale just given the number of transistors they had in their budget even in 2007 to what we have today. I think this is probably a good stopping point, even though we didn't get through everything, and I'm going to want to continue this on Tuesday. Um, as you review this material, as you go check out some of those videos on YouTube, the big picture takeaways from today are just there's been this continued evolution with some pretty key milestones along the way, and then modern graphics processors look roughly something like this, where there are simpler than 381 style CPU cores or CPU like cores. It's a bit of semantics whether you'd call that a core or just an ALU in terms of what it supports. And then a bunch of additional hardware to still effectively support some variant of the rendering task pipeline. And that's what modern GPUs have looked like since that generation. That's what they still effectively look like today. Um, let's leave things here for today, just in the interest of time. And there's just a lot more I'd like to cover. One final question I saw in the chat. So we're connected to connected to a discrete CPU. Um, it's kind of fun, right? I mean, so you'll see how it works. The video I made for MP1 doesn't really describe that at all. But the way it's going to work is we have a workstation that you're connected to for those upcoming SGP design labs. Um, it's a workstation with a GPU on it. So the way it will be working is you'll be running OpenGL. Eventually, you'll be running OpenGL programs on that workstation, and we're capturing all those calls. We're capturing all those OpenGL calls that are happening, and then we're connecting them to our driver. So we're kind of shadowing or mirroring those calls. I feel like I should make I should make a video or something of this because I don't explain this in the video that I created for MP1. And we are capturing all those calls. And so you're going to see two windows at any given time. You're going to see what your NVIDIA graphics hardware thinks the output should be, and then you're going to see what your hardware thinks the output should be. And in a perfect world, you'd have two monitors and they'd be side by side. In this class, one of them is a remote desktop window, right? And one of them is a VNC or VLC window looking at a screen, a camera pointing at a screen. But you have those two windows side by side. So we do have a CPU. It's a Intel Xeon CPU of some sort. You do actually have a GPU already. That's an NVIDIA Kepler class GPU. And you then have, from connecting to that, your implementation of the GPU. So you always have that baseline of how things ought to be. Here's what a real GPU, here's what the $20 billion company's GPU looks like. Here's where the $8,000 semester GPU looks like. And you get to compare those two as you make progress. And that should be fun along the way. So you don't have to actually build any CPU logic for this semester. The CPU is baked. There is a GPU that's also baked. You then get to directly compare the results between one and the other. That's pretty unique. There's no other course in the world, to my knowledge, that does anything like that. So hopefully you get to really enjoy that experience, even if it may be frustrating at certain points along the way. Let's leave things for here for today. I look forward to seeing some progress over the weekend if you have time to make it on MP0. And otherwise, I will be seeing everyone on Tuesday.